Now we get to have friction involved in motion and sliding our boxes. So we're going to go from our frictionless surfaces to something that is a bit more realistic to what you're used to. And so first, let's go ahead and define what friction is. So friction, the easiest way to think of it is like the stickiness between two surfaces. So it is defined as the stickiness or the roughness of a surface, in the force normal. So how hard something is on a surface, or how firmly rather, and how sticky that surface is. And so now the truth is that this, you throw these things out there and we say, oh yay, just use these definitions, and then you can go look online and you'll be like finding all the examples of when this model doesn't apply. And it comes down to the fact that we really don't still completely understand the force of friction. What we do know is that there's two different types. We have the force of friction that is static. And then we have this force of friction that we call kinetic. Can I spell? Yes, I can. So the force of friction, we give this symbol to, or sometimes you'll just see it with this kind of script F. And this script F, you'll see either a static or a kinetic, one of those ways. And the way we define the stickiness is this mu looking thing that is a mu, not a, I don't know what that would look like, maybe an M. This thing here is the coefficient of friction. So the stickier something is, the higher this number is. And probably one of the more common questions I get is, can this number be greater than 1? And one of my favorite things to do is to give you an exam question that has it turn out to be greater than 1. So it's not limited. It can be greater than 1. It just can't be negative, because that would be odd. And we'll talk about that in a little bit more. And so we have two different types of friction. And I think the easier way to think of it is that when something is resting on another thing, this pen, there it is, this pen is made up of molecules. My hand, even though it's just skin and now lots of marker from all my lectures today, is also made up of molecules. So when I have my hand holding this pen, I have an interaction between the molecules in the pen, where'd that go? Molecules in the pen and the molecules in my hand. So the same thing is happening when two surfaces, oh, you are so kind, when two surfaces are in contact with each other. Now, the more they have contact, or the longer they're able to, well, no, think of it as more, not the more they're able to, the stronger that interaction will be. So let me go back to my pen. There's my pen. If I have, dogs, why not? When I have really good contact between these two, what's happening is that that chemical bond, if you will, it's not an actual bond, it's an interaction. The stronger it is, the harder it is to push something, the stronger the force of friction is. And there's a couple of important things, and we're going to work with both kinetic and static. But I want to talk about static here first, because I'm going to give you an equation, and you're going to start using it for everything when it doesn't apply to everything. And that is, I'm going to say that the force of friction is defined as the force normal times mu, where this is the coefficient of friction, this is the force normal, this is the force of friction. And it seems on the surface like it should be true, but let me ask you this. If I'm pushing on this desk and I haven't overcome the force of friction, it's not even starting to slide yet, does my push equal the force of friction? Because if the force of friction is the force normal, so let's just do the force free body diagram for my desk. Here's my desk, there's gravity, and there's the normal. So my force normal equals the mass of the desk times the acceleration due to gravity. My mass, or the mass of this desk is about, I don't know, about 100 kilograms, 98 kilograms, something like that. So this says that I am pushing with, let's just round it up to 100 kilograms. And for funsies, we'll just use 10 for that. So 10 meters per second squared. So what does this say? This says that 1,000 newtons is the normal force. So let's go back to this. I'm pushing on this desk. My face is relaxed. I'm pushing. Somebody at the door. Okay. So again, looking at this, I'm pushing on the desk. I don't know if you can really wrap your brain around 1,000 newtons, but am I really pushing that hard? Because I kind of feel like I'm not putting 1,000 newtons worth of force. So if this always equaled the force normal times the mu, because granted, I don't know what the mu is. So if I'm applying that much force, what does that mean? Let's see. It says that the desk, I have the force of friction going this way, and my force push going that way. So my force push, doing the sum, I'm sorry, I'm skipping steps, force push. And the x, and my force push minus the force of friction. Well, this thing isn't moving. It didn't accelerate. So that equals 0. So my force push then, if I use this definition of the normal times mu, would be like 1,000 newtons times however sticky this thing is. That's a pretty good substantial chunk of friction, or of force right there. Even though it's multiplied by the coefficient of friction, I mean, I'm not even like really trying, I'm just pushing. So my hunch is that my force applied is maybe 5 newtons, maybe. So if that's true, that says that my force push is about 5 newtons, and let's just use like 0.1. So 10 to the negative 1, moving this over here. So this is 100 newtons. So if it were true that this always equals this, well, what's happening here? I'm pushing on it. That gives me that I have a force push this way of 5 newtons and a force of friction coming this way, make it bigger, of 100 newtons. This says that the force of friction is actually accelerating the darn thing. And it's not. My table hasn't taken off running, right? So the force of friction is not making it go. So what is true? So all of this is not complete. This is true. This is true just before it starts moving, just before it breaks loose, just before it moves. It's also true after it starts moving. So those two things you need to ask yourself. If I'm pushing on it and it's not moving, the force of friction does not equal the force normal times mu. The force of friction precisely equals how hard I'm pushing on it. If I'm pushing with 5 newtons, I haven't gotten to this threshold, so it's not moving. It's pushing back. It's a third law of pair. I'm push on it, it's pushing back on me by the exact same amount. The force of friction in this case, as I push on my desk, is precisely 5 newtons. It can't be bigger, because if it's bigger, it's making it accelerate towards me. So for this to be true, and I want you to write that down and know it, that this is true just before it moves, that minute, that split second before it breaks loose, and after it started moving, after it starts moving. So once it's in motion, this is true, and that split second before it gets going. So with that, let's do some practice.